Request Dr. Laurent
Okay.
to
Thank you.
introduce the activities of ISPRS.
Good morning.
Okay.
Let's go ahead. So very good to say that we have about 60 people online. So good morning. My name is Laurent Polidori, and I'm the president of the Commission 3, Remote Sensing of the International Society for Photogrammetry and Remote Sensing. And it's my pleasure today to introduce this webinar. So the first session of a webinar series over July and August on various topics related to remote sensing applications in the field of water, ice, and snow. This webinar series conducted under ISPRS Technical Commission 3 and with the valuable support of the student consortium of the ISPRS is an initiative of Working Group 7 on Hydrosphere and Cryosphere under the chairmanship of Dr. Praveen Thakur and his team, in particular Dr. Vaibhav Garg, sorry for the pronunciation, who is involved in the organization of this webinar. So thank you, congratulations. I will give you the floor in a few minutes, but I would just like to take this opportunity to say a few words about ISPRS Commission 3 and to recall that each commission of ISPRS, each of the 5 commissions established for a 4-year period from 2022 to 26, is organizing its midterm symposium this year in 2024. And Commission 3 symposium will be held in Belém, Brazil in November. It will be the last of the 5 symposia in November 4 to 8. And I just want to recall that if you want to participate, please see the website on the webpage of ISPRS, and the early bird registration is open until this weekend. So don't hesitate to check if you're not registered yet. So I don't want to be longer, and I would like to give the floor to Dr. Praveen, who will now introduce our lecturer and the content of this webinar. So please go ahead. Thank you.
Thank you. Thank you, Dr. Laurent. So this, as Dr. Laurent has said, we are part of the ISPRS Technical Commission 3, and I am chairing the Working Group 7 on remote sensing of hydrosphere and the cryosphere. And this webinar series has been conceptualized after discussing with Dr. Laurent and our internal discussion among the various chair, co-chairs, and our members. And this webinar today is the first topic, topic on remote sensing of snow and glaciers by Professor Dr. Dozier. And from today onwards, every Wednesday, we are organizing 8 webinars covering various aspects of hydrosphere and cryosphere, including the oceans, which we consider as a part of our hydrosphere. So, except one Wednesday, all 8 various speakers who are experts and renowned people in their particular field of expertise. So before we start, I'll just give introduction about the ISRS also, the co-host co-organizers in this webinar series, Indian Society of Remote Sensing. I'm also the secretary of the national body. So our society is the oldest, established in 1969, with the main objective of advancement and dissemination of remote sensing technology in the field of mapping, planning, management, and of natural resources and environment by organizing various seminars and symposia. And we also published Journal of Indian Society of Remote Sensing, which is one of the high impact journals among all the Indian journals. And we have more than 6,328 members. And we have very active collaboration with international scientific societies like ISPRS, for which we are ordinary member with category 8. And also we are member of Asian Association of Remote Sensing. So today, now coming back to the webinar, our first talk is by Dr. Dr. Dozier. So as students of remote sensing, and especially for snow and glaciers, he has been the father figure and the one of the pioneer in this particular field. And Dr. Dozier has been with UCSB faculty since 1974, and he was the founding dean of Bren School. And he has led many interdisciplinary studies, especially in 2 areas. One addressing the hydrological science, environmental engineering, and social science in water and environment. and other is in integration of environmental science, remote sensing with computer science and technology. So, from 1992, he was the senior project scientist at NASA Earth Observing System when the configuration was established. And among various honors, Dr. Dozier has received his career 2009 Jim Gray Award from Microsoft for his achievements in data science, and his selection as a 2010 Nye Lecturer for the Cryosphere group of EGU. And he is avid mountaineer, rock climber, and helped led 6 expeditions to the Hindu Kush range of Afghanistan and dozen of first ascents in those peaks. Story behind the Dozier Dome in Sierra Nevada can also be found in the Super Topo Climbing Forum. So apart from an active and avid researcher, he is also a very good mountaineer who loves not just the science of remote sensing and glacier, but also doing the outdoor and activities. And many of people who work in this world, the snow spectroscopy, especially NDSI, and its how optical properties behave. So he is the one of the founding members and the researchers who gave these theories. And operational snow cover mapping from NDSI, which is most popular indices for snow, as well as the grain size index. Those are the indices which was first proposed by Dr. Dozier. So we are really privileged to have you for this first webinar of our working group, and we give the floor to you, sir.
Okay, well, thank you very much for the introduction. I will point out that this picture in the opening slide is from Sikkim province of India. So it's appropriate, I think, for this presentation to use some information on the mountains in the Indian Himalaya.
Yeah, thank you.
Okay, so, oh gosh, so my slide is not advancing. Okay, well, so there may be a little bit of delay when I click each of the slides. I hope it won't be a problem. So what do we want to try to measure from remote sensing? Well, the obvious one is the extent of the snow. The first question you have is there snow or not? A second issue is we're interested in the albedo of the snow, the fraction of the solar radiation that it's reflecting. We're interested if the snow is wet, because when it's wet, it means that if we add energy to the snowpack that will produce melt. We're interested in the temperature of the snow for the energy balance calculations. And then we're especially interested in how deep the snow is and what its density. And we call the product of the depth times the density to be the snow water equivalent. And if you look at the dimensionality of the equation, that is something that is measured in kilograms per square meter, and that would be the equivalent of 1 millimeter of depth. So snow is important for all sorts of reasons, and I don't want to belabor them here, but nearly 2 billion people get their water resources from the snowpack. And India is certainly a big part of that. In much of the world, the water comes from the mountains. And so therefore, our examination of the snow has to deal with the terrain. Most of the melt comes from the solar radiations. So we're interested, therefore, in the albedo of the snow. And in the mountains also, that every pixel in remote sensing often has other components in it. So we're often interested in the fractional snow cover. That is, what part of the pixel is snow versus what part is something else. So those are the things that I want to try to cover in my talk today. The reason we want to remotely sense snow is that in the mountains, the surface measurements that we make, for example, weighing gauges for the snow, don't cover the highest elevations. And so this is an example of the from my own mountains in the Sierra Nevada. And what we see are this graph of a set of snow sensors in this Tuolumne River basin. And we see that from the snow sensors, most of the snow has disappeared by the middle of July in the summer. And yet we see that even when all of the snow has disappeared from all of these stations, there's still snow in the mountains, and there's still water that is produced from that snowpack. So let me kind of give an outline of remote sensing in general that'll help during the whole rest of this seminar. That one of the ways of characterizing remote sensing is whether it's passive or whether it's active. So in passive remote sensing, it means that the source of the energy that we're measuring is either the sun or the earth or its atmosphere, or now signals of opportunity from things like GPS or communication satellites. Most of that energy comes from the sun, and then some comes from the earth and its atmosphere. In contrast, the other kind of remote sensing is what we call active, where the source of the energy is in the system itself. And in those categories, we include radar, which is typically wavelengths in the centimeter to almost a meter wavelength, or LIDAR, which is light that is bounced off of the snowpack. So I'll cover both of those in my lecture this day. So the first part, the visible through the infrared spectrum, is we're dealing either with radiation reflected from the sun, which is from about 0.3 micrometers to about 5 micrometers. And in this case, we need to consider this big variability in the optical properties of ice over those wavelengths, where ice is highly transparent in the shorter part of that spectrum through the visible up to about 0.7 of a micrometer. It's moderately absorptive in wavelengths beyond that. And then when we get above about 1.5 micrometers, ice is almost opaque. And then the emitted radiation from the Earth and its atmosphere in this part of the spectrum is from 3 to about 50 micrometers. And in this case, ice is absorptive. And so this helps us estimate the snow temperature. And then in the same wavelengths, we also have active remote sensing from LIDAR. So the rationale for looking at this fractional snow cover measurement is that in the mountains, a lot of the snow is going to occur in pixels that are only partly snow covered. And so if you look at on the left-hand image in this diagram, this is the image of the fractional snow cover in the Sierra Nevada of California. And we can calculate the total area of that is about 81,000 square kilometers. If we only consider the pixels that are at least half covered and think of those as all covered, we get almost about the same total area, in this case, about 85,000 square kilometers. But if we consider in the right-hand image, the area of the snow which is only partially covered, that is each pixel less than half, then we see a substantial area. And therefore, if we're trying to model the snowmelt, well, even our best model cannot handle snow that it doesn't know is there. So some various ways, satellites that we've used to measure snow. The thematic mapper, starting in 1982, measures in about 30 meters spatial resolution. It's got a field of view of 185 kilometers and therefore a 16-day repeat pass. And again, you can see this nice map of the snow cover. The one thing that was innovative about this satellite at that time was to include a band out at about 1.5 micrometers where snow is dark, but clouds will be bright because the scattering particle in a cloud is much smaller. And therefore, you can see in this left-hand image in the visible part of the spectrum that it's very difficult to distinguish the snow from the clouds. Whereas if we include this channel around 1.5 micrometers, that you can see that the snow and the clouds are separable. We also use MODIS, the moderate resolution imaging spectrometer. It has a much bigger pixel of 500 meters, but it also has daily coverage. And therefore, we can see the fact that the snow changes fairly rapidly. And what we also see is that the spectrum of snow, which is shown in the lower left diagram, notice that if the snow is clean, then the two upper lines show the blue and the red line show the variation with the whether the snow is coarse or is fine, but then the yellow line and the purple line show what happens when the snow is dirty. And you can see that there's a big change in the visible part of the spectrum that is caused when the snow is dirty. You can also see, if you compare the reflectance of snow to that of vegetation in the upper left, that the snow is really quite different than the vegetation. And similarly, in the upper right, you see the typical spectral reflectance of soil, and snow again is quite different from that. And then that summary slide in the lower right shows that indeed snow is different than the other things that are on the Earth's surface. Okay, so what we can do then with an instrument like this is over terrain, which is very rugged, which we see in the left-hand diagram in the Sierra Nevada. We see the bands that we can use to estimate the snow. And then in the right diagram, we see the fractional snow-covered area. So that's kind of the first thing we want to look at when we try to remotely sense snow, is the extent. Is there snow or is there not? So now we turn to the question of, well, what else are we interested in? Well, we're interested in how rapidly that snow will melt. And what we know is that most of the energy that causes the melt comes from the absorption of solar radiation. So if you see the equation here on the left, the net flux is the combination of the net solar radiation, the net long wave, the sensible heat influx, and the latent heat flux. And then what we see in the bars in the right-hand diagram is the fraction of that solar radiation. Excuse me, I need to plug in my computer. we see the fraction of that solar radiation in all of these environments, in the Himalaya, the Swiss Alps, Antarctica, that the main source of the energy is coming from the sun. And then the graph in the lower left-hand shows the same information for a single site. And so this is over 4 days in the San Juan Mountains of Colorado. And you see the diurnal variability in the solar radiation, and the net flux pretty much matches the net solar. That is showing again that that's the main source of the radiation. The long wave radiation, which is shown in the dashed red line, is generally negative, but continues throughout the night. And then the sensible heat flux shown in the blue line and the latent heat flux tend to mirror one another. That is, when the sensible heat flux is strongly positive, the latent heat flux is strongly negative, because they both depend on the wind speed. Okay, and then if we look at snow, some of it is nice and white and therefore reflects a lot of the energy, but you can see that some of the snow is dirty. And it can happen from dust. It can also happen from black carbon caused by combustion in the urban areas near the snow line. So what we see in this is that the reflectance of snow varies, and it varies for two reasons. So the black line that slopes up from the lower left to the upper right is the absorption coefficient of ice. And you can see that in some parts of the spectrum, ice is really transparent in say, the wavelengths from 400 to about 800 nanometers, but ice is much more absorptive as we get to the longer wavelength. So what that causes, if we look at the set of blue lines in this graph, is that for clean snow, the reflectance varies with the size of the snow grain, but it varies very little in the visible part of the spectrum, because there the ice is so absorbed, or is so transparent. If we add a light absorbing particle like dust to the snow, then that dust mainly affects the snow in the visible part of the spectrum, because that's the part of the spectrum where the ice itself is really transparent. And so adding a little bit of dust or a little bit of soot to the snow will really make a big difference. But when we get to wavelengths beyond about 1,000 nanometers, then we see that the dust really causes very little effect on the reflectance, and there the reflectance is mainly due to the grain size. And so the text now in this slide kind of emphasizes this, that the dust or the soot decreases reflectance in the visible part of the spectrum, and then in the near infrared and the shortwave infrared part of the spectrum, the larger grains, as the snow metamorphoses, causes the reflectance to decrease. So there's these two mechanisms that control the albedo, and we want to be able to separate those. So some examples of this that we try to do then with remote sensing is we try to estimate the grain size in the snow, and then we also want to estimate the degree to which contamination has affected the albedo. And so these images show the area of Mount Shasta in Northern California, and which is a volcano. So it's got a conical shape to it. The upper left image shows a Landsat image. The upper right image shows the fractional snow cover, the extent of the snow. The lower left image shows the grain radius of the snow, and then the lower right image shows the albedo of the snow. And you can see there's a lot of variability in the brightness and therefore in the fraction of the solar radiation that the snow absorbs. Okay, so why does the grain size affect the albedo? Well, the answer lies in the optical properties of ice, and we express those by the index of refraction, which is a complex number. So the real part of the number, n in the equation, explains how the light bends as it goes through a block of ice. And then the imaginary part is the absorption coefficient, and that tells you the rate at which absorption takes place as a beam of light passes through the snow cover. And the reason in this differential equation that we divide by wavelength is that way the absorption coefficient can be a dimensionless number. And if you solve that differential equation, you get this exponential decay, which is shown in the lower right. So one way of characterizing that is you can calculate a scaling length to see the length at which light passing through a substance decays to the fraction e to the -1. And so that's shown in this graph here. And so the absorption coefficient of both ice and water are shown in the two dashed lines that slope from the lower left to the upper right. And you can see that the absorption coefficient over the spectrum in the solar wavelengths, varies by 7 orders of magnitude. And then if we translate that to the scaling length, which is shown from in the blue and the red line, that's for ice and for water, that slopes from the upper left to the lower right, we can see that the scaling length varies from meters to micrometers. And so in the visible part of the spectrum, it's, ice and water are very transparent. And so if you're swimming in water and you have goggles, you can see a long way. And similarly, if you were frozen into bubble-free ice, you would also be able to see a long way. But if you get further out into the spectrum, then that scaling length becomes smaller, and therefore the size of the snow grain makes a difference, because that controls the path length that the radiation is going to get through one of the grains. And so this effect then of these light absorbing particles in snow is that if we look at the solid lines in this graph, this is the net radiation of clean snow. But then if we add dust or soot to the snow, then we get a much different spectrum of the reflectance. So for the clean snow, the net radiation peaks in the 800 to 1700 nanometer range. But if the snow is dirty, then this radiative forcing caused by the light absorbing particles means that we're changing the reflectance in the part of the spectrum where most of the solar radiation is occurring. And so it makes a big difference. So why is this important? Well, one of the things we look at is, or one of the questions is, what caused the end of the Little Ice Age when all the glaciers receded? And if we look at the graphs on the left-hand side, is that since about 1800, there really hasn't been much of a change in precipitation. And what we see in the graph in the lower left is that really the warming that has occurred mostly since about 1950. And yet, if we look at the graph on the right, we see that the glaciers in the Alps of Europe started to retreat about 1850 or so, before the temperature had gotten much warmer. And the reason for that is that if we look at the ice cores, we can see that the concentration of black carbon in the ice really started around 1850 with the Industrial Revolution that occurred. And so the retreat of the glaciers was caused by the black carbon in the ice, not so much caused by warming temperatures. Okay, so for trying to isolate this and trying to sense these properties from remote sensing, I want to show some examples from the campaign in India for the NASA Airborne Visible and Imaging Spectrometer. And so this was in the Himachal Pradesh province of India. You can see the Landsat image is on the upper left. You can see in the lower right is an image that shows the elevations. And you can see this is a very high area, that the elevations are ranging from 3,000 meters to 6,000 meters. And then the image on the upper right shows the flight lines from the NASA aircraft during this campaign, which was done in conjunction with ISRO, the Indian Space Research Organization. So one of the problems in this, in trying to solve these, to interpret these properties, is that we are inverting the radiative transfer equation. And so computationally, this can be a difficult problem. And so what we do to use some machine learning for this is to train the algorithm on a sample of pixels, which we can either use super pixels, or we can identify pixels which are similar to one another. And therefore, for each sample, we invert the reflectance models, and then we use those to train a machine learning model. And we can do this over time and improve the model. And so what we can do with this is we can identify for this flight line in the Indian Himalaya the fractional snow cover in the upper image, and then the albedo of that snow in the lower image. And therefore, we see again the range of albedos in this. We can also see what's causing the change in albedo. The upper image here shows the effective grain radius of the snow in micrometers, and then the lower image shows the concentration of the dust and how it varies over this terrain. Okay, in this, there is one thing that we have to worry about, and that is the difference between what we call the intrinsic and the apparent albedo. And the effect that a rougher surface is going to absorb a little bit more solar radiation because in these ablation hollows, the sunlight bounces around a little bit before it reflects, and then in one of those bounces, some of it can be absorbed. So what you see in the left-hand image is our experimental site in the Sierra Nevada where we measured this. And what we see in the right-hand image is the amount of absorption in the field of view of the down-looking radiometer. Okay, so let me point out some other things. With regard to glaciers, well, for glaciers, there's really two things we want to worry about. One is the effect of the snow on the glaciers and how fast it melts, but the other is where the glaciers are. And for this, to keep this lecture a little bit shorter, I simply wanted to point you to the Randolph Glacier inventory that has tracked the size of the glaciers, of about 500,000 glaciers all over the world. And you can see that this is an example from the Himalaya, just north of where you are, from the glaciers in the Mount Everest region. And I would refer you, I guess, first to the website for this work. And then also they have, in fact, published a book on the findings from this project trying to inventory the glaciers all over the world. Okay, so let me now switch to the thermal infrared part of the spectrum, which is looking at the temperature of the snow. And what we can see from this, if we look at the snow and the trees, is that at the surface, at least, when we measure the temperature, is that the trees are going to be warmer than the snow. And so if we're trying to calculate the energy balance of the snow cover, we need to be able to separate the temperatures of the snow and the trees. And so this is the kind of variability we see. We've measured this not only with MODIS, but also with an aircraft where we look at the variation in temperature over an area. And what this shows in the left-hand image, that square in red shows one of the MODIS pixels, but then the finer image shows the temperature based on the aircraft. And what we see, of course, is that the trees, which you can see in the right-hand image, are in fact warmer than 0 degrees C because they're absorbing the solar radiation, whereas the snow is much colder. So one of the questions, and really this is a research topic that we're really still working on, is can we, in remote sensing, separate the temperatures within a pixel into indicating, for example, the difference between temperature of the vegetation versus the temperature of the snow. And this is based on a paper that I wrote in 1981, looking at burning flares from oil platforms in the Red Sea. but we're now looking at this to see if we can use this to detect the separate the temperatures of snow and trees. And we can see that even in pixels that in this case were over a kilometer in size, we could see fires in the oil wells that were only meters in size. So the mechanism for doing this is that the Planck equation has a different slope at different wavelengths. And so if you have a infrared sensor that is measuring at around 4 micrometers versus one that is measuring at around 12 micrometers, you can use that to separate the temperatures of two different surfaces. Okay, going on to the next topic, we still want to be able to measure how much snow there is, either the depth or the snow water equivalent. And one way of doing this in the this optical part of the spectrum is to use LiDAR. And so basically what a LiDAR does, it shoots a pulse of light, in this case from an aircraft down to the surface, and then measures the time that it takes to come back to the sensor. And therefore you can measure the elevation of the sensor above the surface. And if you do this, first of all, during the summer when there isn't any snow, and then during the winter when there is snow, and you look at the difference between those two elevations, and that tells you how deep the snow is. And so this is done by, it's carried out in the Sierra Nevada by what is called the Airborne Snow Observatory, which measures for the purpose of estimating water resources in the Sierra. In 2015, we had a very dry year, and you can see in this case that the snow water equivalent is peaking at about 0.5 meter or so. And then in 2016, we had a very wet year, and you can see that not only is there a lot more dark blue in this image, but there is also the scale has changed. If you see in the lower left, which before in the previous image, the scale only went to about 0.5 meter. Now in 2016, which was more of an average year, it goes to 1 meter. And then in 2017, which was a very wet year, then that scale, as you can see in the lower left, goes to 3 meters of snow water equivalent. Okay, switching gears, we want to look at the microwave spectrum, which is generally there. We use frequency to measure the radiation rather than wavelength. And the reason for that is as a wave passes through a substance, the speed slows down and the wavelength changes, but the frequency stays the same. Hence, that's the reason that we can measure the radiation in frequency. And the frequency is just the speed of light divided by the wavelength. And so now we get to a sort of a different concepts in these two different parts of the spectrum. So what I've covered so far in the visible and the near infrared and the infrared is that the grains and the separation between the grains is large compared to the wavelength, and therefore we can treat this as a scalar radiative transfer problem. We typically use Mie scattering to estimate the scattering properties of the individual grains. In these wavelengths, the optical properties of ice and water are pretty similar. In this case, we can't really see through clouds. And in the snow itself, that radiation is really only penetrating a little bit into the snow before it reflects. So maybe 30 centimeters in the blue part of the spectrum, and in the near infrared part of the spectrum where the ice is more absorptive, that penetration is really measured in millimeters. Now, contrast this, if we look at the right part of the slide, is in the microwave. And now the wavelength is bigger than the grains and the separation between them. And so therefore, rather than treating the snow as a set of ice scatterers within a transparent medium, we instead consider the medium to be the snow itself. And we look at the extinction per unit volume of the snow. The other thing we find in this part of the spectrum is that ice is about 80 times more water is about 80 times more absorptive than ice. And so when the snow gets a little bit wet, then the microwave signature really changes. The big advantage of the microwave is that it penetrates through clouds and it penetrates through the snow itself. And therefore, it tells you something about the pack itself rather than just what's going on at the surface. I see there's some questions here. Okay, let me look at. Let me get back to these and at the end. Okay, I don't know. Okay, so my slide seems to be frozen again. What's going on? There we go. So this shows in the microwave the difference in the optical properties of ice versus water. Both the real part of the refractive index varies, with water causing the wave to slow down a lot more than ice. And then the imaginary part, which specifies the absorption, is also much greater in water than it is in ice. And therefore, wet snow is going to give us a different signature than dry snow. So therefore, rather than thinking of the snowpack with ice, air, and liquid water and light absorbing impurities, in the microwave, we simply think of snow as the medium, and it has optical properties that are properties of the snow itself rather than the constituents. The other thing to point out is that the advantage of the microwave is that the signal integrates the entire thickness of the snowpack, or if you're looking at forests or soils. But ironically, the disadvantage of microwave remote sensing is that the signal integrates the whole thickness, and therefore the analysis can become more complicated. The other thing about the microwave, we characterize the microwave by these letters that correspond to different frequencies and therefore different wavelengths. And you can see from shorter wavelengths in the millimeter going from W band all the way down to P band. This unfortunately makes microwave remote sensing a little bit opaque to the general student. And the reason is that these designations were designed during the time radar was invented, which was really during World War II. And engineers wanted to be able to kind of talk in code. So the fact that these letter designations are confusing is because they were designed to be confusing. But one thing to characterize here is that NISAR, the NASA ISRO radar satellite that's going to be launched pretty soon, it works out, it's at L-band. So it's got frequencies from 1 to 2 gigahertz and wavelengths from 15 to 30 centimeters. Okay, so there are really two kinds of microwave remote sensing of snow. One is the passive microwave. And so what this does is it looks at the microwave emission that is emitted from the Earth. And absorption by ice itself is low when the snow is dry. And so there's very little emitted radiation from the snow itself, and therefore the underlying soil is the major source of the microwave emission. The snow scatters, and therefore it attenuates the upwelling radiation. And so therefore more snow means more attenuation, so less emitted radiation from the snow systems. And the attenuation is greater at the higher frequencies. And so therefore we can look at the microwave emission from different frequencies, and that'll tell us something about how much snow it is. And then the caveat is, because water is so absorptive, is that wet snow looks much like soil in passive microwave. So if we look at the Planck equation for the what's emitted at various temperatures, we see that the temperature itself doesn't make much of a difference at these frequencies. And you can see for the different lines for 288, 250, and 300K in the wavelengths where most of the passive microwave is measured, is those temperatures are very small, differences are very small. And so what really causes the change in the microwave emission is the emissivity of the system rather than its temperature. And so we can retrieve these, the amount of snow by looking basically at the difference in temperatures between a couple of frequencies. Now, the only issue with these, and the disadvantage of passive microwave, is there's very little energy at these wavelengths, and therefore the pixels have to be very large, typically on the order of 25 kilometers or so. So you're really averaging the signal over different values. Secondly, is that the microwave emission runs into saturation. So, for example, you see in the left-hand diagram that the for low amounts of snow, for the snow water equivalent less than 150 millimeters, that there's this very nice correlation between the ground measurements on the x-axis and the microwave estimates on the y-axis. But then in the right-hand diagram, you can see that that relationship becomes asymptotic. That is, once you get above about 150 to 200 millimeters of snow, the signal gets pretty flat. So therefore, it's very useful for measuring rather shallow snow over big uniform areas, but it's not so useful for measuring snow in the mountains. And you can see this in the Sierra Nevada if we've compared the microwave measurements from AMSR-E with methods that we've calculated where we reconstruct the snow cover based on the energy balance calculations and using the optical measurements to see when the snow has disappeared, is that if we compare the snow water equivalent measured by these techniques with the full natural flow in the streams, we see that in the microwave, in the left-hand image, the red line on the left it's pretty much flat vertically. That is, there's very little relationship between the amount of water that we're getting from the amount of snow that we're measuring. And then in the right-hand diagram, we're seeing that the reconstructed snow water equivalent from our method is it doesn't correlate very well with the microwave measurements. So basically, the issue is that in the mountains, the passive microwave isn't very useful. Okay, so what we can do is instead of looking at passive microwave, we can look at active microwave. That is radar imagery of snow. And so we're looking at, we can look at non-imaging radar, which are altimeters and scatterometers used over big areas, or synthetic aperture radar, which again, we're eagerly awaiting the launch of NISAR in the next within the next year. So in this case, there's two ways of looking at the radar signal. And one of them is to look at the backscattering. And there we have a problem in that a lot of it depends on the surface roughness. So if the surface is smooth, you get very little backscattering. But if it's rough, you get more backscattering. You get in the areas where there are trees, you get a double bounce reflectance, and so you get a signal. And then you also get some volumetric scattering that doesn't come from the surface, but that comes from the volume of the snowpack. And so basically, in the radar wave in the snowpack is that in the longer wavelengths, like C-band at about 5 centimeters, or L-band, which has a wave of about 20 centimeters, it's not very sensitive to the snow. And so the main contribution to the backscatter is the ground beneath the snowpack. Whereas in the shorter radar wavelengths, we do get more of a more sensitive to the snow properties. However, what turns out to be really useful in these longer wavelengths, and we're eagerly awaiting what goes on with NISAR, is that because the radar wave passing through the snowpack slows down, if we compare the phase of the return signal with what happens when there isn't snow, or when there's a change in the snow, that we can, in fact, estimate how much snow there is from interferometry. And this is something we're very eager to look at when NISAR is launching. And what we see from the equation in the lower right that this change of phase caused by the snow is caused both by the change in depth, but also by the permittivity of the snow, and that depends on the density. And so what you have are two things in the equation that are pushing the phase in the same direction. And so it turns out that, well, first of all, the fact that this change in the permittivity is nearly linear is that what we can see is that we can retrieve the snow water equivalent without knowing the depth or the density. And so you can see that it's only at very low densities that there's any sensitivity. And then pretty much the signal is just based on the snow water equivalent itself. Now, the problem is you can only measure the phase to a resolution of 2 pi. And so therefore you have to be able to unwrap the phase. And so with L-band in the middle figure, which we'll see with NISAR, is that at something around a little bit less than 200 millimeters of SWE, we'll have a phase unwrapping. And so we need to be able to guess the amount of snow sort of within that resolution by based on the weather that's occurred. So in a sense, the longer wavelength is better. We can also get something from multi-frequency radar. And this was, the problem is the only really multi-frequency radar we flew was from the SURC mission back in 1994. But we had some nice results. The only problem is this was just a 10-day mission, and it would be too expensive to fly a multi-frequency radar. We can also just use the radar to map snow and ice, even during periods when there's cloud cover. And this was an experiment that we did over the Mount Everest region back in 1998. And because the water affects the reflectance, the radar properties of snow, we can also use this with different polarizations to estimate the water content in the surface layer. Okay, so I'm pretty much at the end of my time here. There's some things I didn't cover. One is the GRACE satellite, which can measure the mass of the water within the field of view, although it's a very large field of view of about 400 kilometers. And then I'm looking forward to some other lectures in this series of webinars, particularly of the NISAR mission, which has interferometric radar. And then we're looking at spectrometers that will fly in the future. And then I've also got some references to some review papers that cover some of what I've talked about. And I think I'm done. So let me stop sharing. And let's see. It looks like I have some questions. How do you want me to handle this, Dr. Garg?
Yeah, first of all, thank you very much, Dr. Dozier, for a very comprehensive lecture on this remote sensing for snow and glaciers. So you have covered snow cover, glacier, the energy balancer for snow melt, snow grain size, effect of contamination on snow reflectance, glaciers, and you have covered all the technology, optical, lidar, hyperspectral, microwave, very comprehensively discussing the physics behind all of them. So yes, we request our participants to post their queries. We will take 2 to 4 questions, relevant questions on the topic. So I request all the participants to post their queries on the question answer dedicated option here given at the bottom. Sir, we have received 2 questions. I will read them and I request you to answer them. So this is the simple question from Mr. Karan Shah. What is the impact of air temperature in the ice sheets or glacier movement, or say ice sheet displacement? Because air temperature has its impact on surface ice melt, so does it contribute in the ice movement?
Well, I guess my answer is, remember that air temperature doesn't have much of an effect. It's the other components of the radiation balance that have the major effect. That said, we can see with the ice, particularly from warming of floating ice from the ocean below, that it has an effect on the plasticity of the ice and therefore on its rate of movement.
Yeah, correctly, sir. Now the next question is, sir, on your slide which you have shown on the fractional snow cover. So how is fractional snow cover computed from MODIS? Is it based on the empirical relationship between NDSA and the fractional snow cover? Could you please elaborate?
No. I invented the NDSI. I think now we tend to use spectral mixing approaches, and the references that I gave have a lot of discussion of that.
Yeah.
So yeah. So like I said, I invented the NDSI. I would recommend that you not use it so much. It is the thing about the NDSI is you can differentiate between snow and clouds, and therefore it's a very effective snow mapping tool. But it doesn't tell you very much about the albedo of the snow, which is what we're really interested in. Okay.
Yes, thank you. Honor for us to have you on board for this particular webinar. And I would like to thank Dr. Laurent, Dr. Praveen Thakur, and special thanks to Nick, the representative, the vice president of the Students Consortium of ISPRS. Dr. Laurent, would you like to add something?
No, thank you. Thank you for the very, very interesting conference, and it's a very great pleasure to see that this webinar announces a very interesting series of webinars in the next weeks. Thank you.
Thank you so much. And it is a great initiation of this webinar with the lecture from Dr. Jeff.
Yeah. Okay.
Yeah, thank you so much, sir. So we can leave.
Well, thank you for inviting me. It's very interesting.
Yeah, thank you so much. Yeah.